By far, we discussed implementation of selections, sorting, and joins. Let's take a quick look at algorithms for other operations such as duplicate elimination, projection, set operations, and aggregation. Let's start with duplicate elimination. Remember usage of distinct in SQL. When we use distinct, we are trying to eliminate the duplicate tuples from the output of our query. Duplicate elimination has application in implementation of other operations as well. One of those operations we will see shortly is projection. Duplicate elimination can be implemented using hashing or sorting. The algorithm based on hashing is very similar to what we did in hash join. The relation is partitioned using a hash function, and this function is on the basis of the whole tuple. Then, each partition is read in, and an in-memory hash index is built for it. In building the hash index, the duplicate tuples will be discarded. This is done by ensuring a tuple inserted only if it is not already available in a bucket. The algorithm based on sorting will sort the relation based on the values of the attributes of the whole tuple. This will cause the identical tuples to appear next to each other. We can then keep one and remove the rest from the output. To reduce the cost of operation in the algorithm based on sorting, the duplicate elimination can happen as a part of the sort step. For example, when performing the merge in the external sort merge algorithm, the writing of the duplicate tuples to the output can be eliminated. Projection is selection of certain attributes from a relation set of attributes. In relational algebra, we depict it with pi accompanied with L containing the list of projected attributes, or the comma-separated list of such attributes provided. Projection algorithm is implemented in 2 steps. In the first step, we remove unwanted attributes from the tuples. This could be performed as we read the relation R into the memory buffer. However, depending on the removed attributes, we might end up having duplicate values on the remaining attributes. Let's see this on the students table depicted. If we only project the attributes school and GPA from this entire table, we will have duplicate output tuples. For example, the tuple with SID 1001 has a school as SFU and GPA as 3.2. The tuple with SID 1005 also has exactly the same values for both of the projected attributes. We might actually want all duplicate values and can specify that in our query. But when we do not want duplicated values as a result of projected attributes, the second step in projection is to remove such remaining attributes. This step can be implemented similar to duplicate elimination on the attributes remaining in the output tuples. It can be implemented using sorting or hashing, and exact same steps of duplicate elimination are applicable for the set of selected attributes available in the output tuple. Set operations include product, intersect, union, and difference. They all can be implemented as variants of a join algorithm. As we discussed in our join algorithms in the enumeration of cross product for join, product operation can be seen as a special case of join with no join condition. Therefore, same algorithms can be applied for cross product. Intersect can also be seen as a restrictive special case of join, requiring equality on all fields. Union and difference can be implemented using algorithms based on sorting or hashing. Let's first discuss implementation based on sorting. For sorting-based implementation of set operations, a variant of sort, merge, join after the sort step can be used. The general steps are first sorting a relation R using the combination of all fields. Then sorting relation S using the combination of all fields. The last step is scanning the sorted R and S in parallel and merging them while eliminating the duplicates. The only difference with the join is the condition for merge is the condition of the set operation for all fields, and not the join condition on join attributes. This will be merging tuples while eliminating the duplicates in R and S for union, and ensuring the tuples in S do not appear in the result in difference. The algorithm based on hashing is also very similar to hash join. In this algorithm, we first partition R and S using a hash function h. Then each partition is processed and an in-memory hash table using a hash function h2 is built. The probing step then ensures adding unique non-duplicate entries from each table for union and removing the found tuple in the second table for difference. Remember SQL queries containing aggregate operations such as average, minimum, maximum, sum, and count. To evaluate these operations, we can implement the algorithm as a simple scan of the entire relation while building the aggregates. This only requires maintaining some running information about the scanned tuples, which is straightforward. For example, keeping and maintaining a counter for the tuples with the attribute we are counting while scanning the entire relation. However, the situation is different if the group by keyword is used with the aggregation. If group by keyword is used, we need to group the values on the aggregate attribute before producing the result. This adds an additional step to the algorithm for performing the grouping. The tuples should be grouped based on having the same value on grouped aggregates. Therefore, to implement this, if there's an index available, we can use it for equality search and apply the aggregate on the result for each group. If there is no usable present index, we can apply sorting or hashing algorithms we saw before to find the groups of the same values. We can then follow the application of the aggregated scan on the groups as we would for the entire relation.